The Intergovernmental Panel on Climate Change has come up with a number of emission scenarios. What these are not predictions of the future, but just scenarios of different possible trajectories for global emissions of carbon dioxide from burning of fossil fuels. If we look at these scenarios, what we see are different possible trajectories. The very high scenarios show continued growth in fossil fuel use, so that by the end of the century, we're emitting somewhere between 25 and 30 billion tons of carbon as carbon dioxide per year. In the lower scenarios, the world transitions from largely a fossil fuel-based energy economy to a much reduced fossil fuel use, and emissions actually decrease sometime around mid-century, reducing to maybe 5 or 6 billion tons of carbon per year by the end of the century. If one takes these different emission scenarios and then runs them through a carbon cycle model that describes the uptake of carbon in the land and in the ocean, and also how changing climate affects the carbon uptake, one can predict what the atmospheric carbon dioxide concentrations would be for these different emission scenarios. You can see that they range from about 500 parts per million CO2 by the end of the century in the very low emission scenarios to as much as 900 parts per million CO2 in the very high business as usual scenarios. So let's take a look at these scenarios and try to figure out what's actually driving this increased use of fossil fuel. In the early 1970s, John Holdren, who's now President Obama's science advisor, and Paul Ehrlich, a biologist at Stanford, wrote a paper that describes a simple way of thinking about how different environmental impacts are affected by ultimately drivers like population, economic growth, and changes in technology. Their paper is sometimes referred to as IPAT from the basic equation they wrote, which is just that impact equals population times affluence times technology. We can apply this equation to any sort of environmental impact. We could think about this in terms of pollution or in terms of overfishing or any other environmental problem. But if we apply it to greenhouse gases, we can write a very simple equation that just says that the emissions of carbon dioxide, the major greenhouse gas, equals the number of people, the population, times affluence, which is just the GDP per person, times the technology, which we're going to define as the emissions per GDP. Now, step back and see that this is just an identity. It's true by definition. If you just take all of the terms and cancel them, you see that you're just getting emissions equals emissions. So in some ways, there's nothing very profound about this. But actually breaking it out into these different terms actually can lead to a very important way of understanding what's ultimately driving these changes in emissions over time. If we take the population term first, this was the subject, of course, of Paul Ehrlich's book in the late 1960s, The Population Bomb. This book predicted gloom and doom for the world because of overpopulation. In particular, it said that India could never have more than 200 million people because they would starve. They wouldn't be able to feed themselves. Today, there's over 1 billion Indians, and they're actually the 4th largest exporter of rice in the world. So something was wrong about Paul Ehrlich's predictions. What was it? Well, here's a cartoon that's typical of attitudes towards the population bomb. This shows the population bomb landing but never exploding. And certainly some criticism of Paul Ehrlich is fair. But if you actually step back, Paul Ehrlich may have been wrong about the timescale, but ultimately he may not be wrong about what's actually going on. So if we ask why was Paul Ehrlich so wrong about his predictions in the population bomb, the answer can be explained partly because of the work of just a few people. 2 of them are German chemical engineers, one named Fritz Haber and the other named Karl Bosch. They both received Nobel Prizes in different years for their work showing how you could artificially fix nitrogen and create nitrogen fertilizer. So our ability to take nitrogen from the air, N2, and make it into ammonia or other forms, urea, that we could use to fertilize crops, played a major role in our ability to expand agricultural productivity and feed the world. The second major hero is a man named Norman Borlaug. Here he is near the end of his life. He died in 2009. And here he is in Mexico in the 1950s, where he worked on wheat. He was an agronomist who studied how we could increase wheat yields. And one of the things he discovered was dwarf wheat, essentially a form of wheat that grew very short. It put less energy into the stems and more into the fruit. It also didn't fall over as much, and therefore it increased wheat yields dramatically. From the approach that led to dwarf wheat, we ultimately derived other forms of high productivity strains of crops, including dwarf rice and a variety of others. And so as a result, wheat yields and other types of crop yields have increased dramatically around the world since the 1950s. This increase in agricultural productivity, what's sometimes called the Green Revolution, is the reason why Paul Ehrlich's predictions were so wrong, why we were able to feed the world without having massive starvation. But you can also ask whether this technological solution really solves the problem, or does it just postpone the problem? Here's a quote from Norman Borlaug from his Nobel Peace Prize acceptance speech in 1970. "The Green Revolution has won a temporary success in man's war against hunger and deprivation. It has given man a breathing space. If fully implemented, the revolution can provide sufficient food for sustenance during the next 3 decades, but the frightening power of human reproduction must also be curbed. Otherwise, the success of the Green Revolution will be ephemeral only." This is now more than 40 years ago. What Borlaug was saying was that the Green Revolution could buy us some time, but ultimately couldn't solve the problem of overpopulation. And that if population continued to grow, we would still need to find new ways of increasing our food productivity to actually feed the world and prevent massive starvation. So you could ask the question whether the Green Revolution really saved hundreds of millions of people, but allowed population overall to increase to the point where now billions of people are facing the same challenges going forward. There's no question that population growth has had a huge impact on the Earth's environment, including the Earth's climate. If we only had 1 billion people on the Earth today, the climate problem would not only be much smaller, but would be much more manageable. But we don't. We have 7 billion people today, and heading towards 9 or 10 billion by mid-century. Most demographers project that population will plateau around 9 or 10 billion and then slowly subside in the latter half of the century, although some disagree and think that population will continue to rise. But if we go back to the iPad equation, we actually see that population growth going forward is actually not the biggest driver of climate change in the future. If we look at this simple identity, the population change is just going from 7 billion people today to maybe 10 billion people by mid-century. That's not even a 50% increase. Affluence, on the other hand, is projected to grow much more quickly. If we look at the affluence term, most economists predict that the world GDP will grow by about 3% throughout this century. What that means is by mid-century, when population has peaked at about 30 or 40% higher than today, GDP will be at least twice and possibly as much as 4 times higher than we are right now. So it's really affluence that's the big driver of the increase in emissions, not population growth. That isn't to say that population isn't important. Clearly, it would be much easier to reduce emissions if we only had 1 billion people instead of 7 billion people. Another important factor to remember is that most of the increase in population is going to be in the poorest areas of the world. And these are people who actually don't use much energy. They don't consume many fossil fuels, and therefore they're not responsible for many CO2 emissions. So overall, the emissions increase is really due to the people we already have getting richer, not an increase in overall population. And then if we think about the final term, the technology term, this is perhaps our one salvation. We know that populations will increase this century, and we also know that people will continue to get richer. At least we hope they will, because it will lead to much greater quality of life and elimination of some of the great tragedies of the world associated with extreme poverty. So it's really the technology term, the potential to reduce emissions per unit of GDP, where the solutions actually lie. We have to decrease the emissions intensity of our economy. We have to decrease the amount of greenhouse gases we produce with every unit of economic activity in order to cancel out the effects of both economic growth and population growth. In looking at the IPCC scenarios that talk about different energy technologies, different population growth rates, different economic growth rates, they result in different emission scenarios that lead to various outcomes. On the left, you see those different emissions scenarios from the IPCC, and on the right, you see those scenarios run through a simple carbon model that then lead to a prediction of atmospheric carbon dioxide concentration levels. The scenarios range from essentially stabilizing carbon dioxide at very low levels, 500 or 550 parts per million, up to CO2 continuing to grow well past 1,000 parts per million in the future. Over the past several decades, there have been many attempts to try to look at what type of energy technologies might be required to follow these different scenarios in terms of energy consumption and ultimately greenhouse gas emissions. Here's an example from the 1980s from the Pacific Northwest National Laboratory. What it shows is essentially a scenario for how to stabilize atmospheric carbon dioxide at 550 parts per million, roughly double the pre-industrial level. In this diagram, on the y-axis is plotted carbon emissions, and on the x-axis is time. Now, what you see is this big gray area. That's the amount of energy we got from fossil fuels, essentially, that would be continued to be emitted to the atmosphere. So those are the carbon emissions coming from fossil carbon, from oil and gas and coal, that would be continued to be emitted and would allow you to stay under 550 parts per million. The upper part of the curve is really the total carbon emissions if we were to continue to use oil and coal and gas. And all the different colors, those different slices, are essentially alternative technologies that stop using fossil fuels or mitigate their use and don't let the greenhouse gases into the atmosphere. So for example, what you see here is the green slice is biomass. Biomass might be replacing biofuel, for example, or the yellow slice is solar. The thin blue one is nuclear. The pink slice, which is very large, represents end-use improvements in technology. That's essentially energy efficiency, making our homes more efficient, our toasters more efficient, our cars more efficient. And then the light blue slice represents carbon sequestration or carbon capture and storage, essentially using fossil fuel, in this case probably coal, to make hydrogen, and then taking the carbon dioxide before it gets to the air and injecting it underground in a reservoir where it would be stored safely away from the atmosphere. In 2004, Steve Pacala and Rob Socolow from Princeton published a paper in Science that was called the stabilization wedges. And this was a very similar exercise to what had been done before, but it simplified it and made it really accessible to the broad community. The impact of this paper on our community has been huge, taking a very complicated problem of how do you mitigate climate change by reducing greenhouse gases with all sorts of different energy technologies and trying to simplify the math down to some very simple geometries in this figure. What this shows in blue is the 500 parts per million stabilization scenario. So this would be a scenario that essentially allows atmospheric CO2 levels to stabilize at 500 parts per million. The upper curve is the business as usual scenario, essentially one of the different scenarios that has the world continuing to use fossil fuels and continuing to increase its carbon dioxide emissions. And the area in green is essentially the need, if we're going to stabilize CO2 at 500 parts per million, the need for non-fossil technologies or non-greenhouse gas emitting technologies that would replace that energy demand. What Steve Pacala and Rob Socolow did was take this green field, which represents the technology innovations that are needed to replace fossil fuels, and divide it into 7 wedges. Each of these wedges, starting in 2004, represented essentially 0 emissions reductions, but in 2054, 50 years later, would each be 1 gigaton of carbon emissions equivalent. And so the cumulative emissions reduction was about 7 gigatons of carbon per year. So the key aspect of each wedge is that they can start small, but ultimately they have to steadily grow until they can actually represent 1 gigaton of carbon by 2054. In their paper, they provided 15 examples of existing technologies that they thought might be able to scale and provide one wedge, essentially 1 gigaton of carbon reduction by 2054. Examples include energy efficiency for automobiles, switching from coal to gas for large power plants, building lots of nuclear power plants, building many, many windmills, building lots of photovoltaics, and a variety of other possibilities. In thinking about how to mitigate climate change by reducing greenhouse gas emissions, there's another important observation about the climate system that is sometimes misunderstood by the climate policy community. In 2009, Miles Allen from Oxford and his colleagues published a really beautiful paper in Nature. And what they showed was that the peak warming from climate change, the kind of full climate response of the Earth system, really responds to cumulative emissions integrated over the next few hundred years. It's relatively insensitive to the exact emissions pathway over that timescale. So you could look at a variety of scenarios where you might reduce emissions quickly in the beginning and then the last 50% of emissions take a long time, or you could reduce emissions very slowly in the beginning and then reduce them very, very quickly. What really seems to matter to the Earth system is the total amount of carbon returned from the Earth as fossil fuel to the atmosphere as carbon dioxide. On longer timescales, if you release that carbon dioxide over thousands of years, then other processes start to come in, like the timescale of the uptake of the ocean. But in general, over the next couple of centuries, what really matters is the cumulative CO2 emissions. Now, this is really important because it reminds us that we have to get to essentially zero greenhouse gas emissions, essentially replacing fossil fuel entirely. We're not talking about a 10% reduction or a 20% reduction or a 30% reduction. The problem is really about how do you get to extremely low emissions in the distant future. Now, short-term emissions reductions are a very important part of that. There's no question that emitting less carbon dioxide today is a good thing for the Earth. We have to make sure that we don't lose sight of the long-term goal and balance short-term efforts to reduce emissions over the next decade or two with the kind of continuous efforts we need to transform technologies that will ultimately lead to getting off fossil fuels entirely in the future. One of the problems with the Wedges framework is that it purports to solve the climate problem for the next 50 years. But of course, in the context of what Miles Allen showed us, that the climate response really depends on cumulative emissions. Stabilizing atmospheric CO2 levels really isn't sufficient. Ultimately, what the climate system cares about is getting rid of all greenhouse gas emissions and keeping the cumulative emissions we release over the next century or two to a bare minimum. So the Wedges puts us on a path towards that solution, but doesn't actually solve the problem. I think it's pretty clear that these technologies that were examples of Wedges may be able to scale up to get 1 gigaton of carbon reduction by 2050. But the real question is, can they keep scaling? Because to solve this problem, they have to keep growing and ultimately eliminate fossil fuel use in the future. So while we may have existing technologies that can solve the problem for the near term, in the long run, there are probably new technologies that are needed to ultimately displace fossil fuels from our society.